Hi, in this video I want to connect the electrostatic concepts we've been talking about so far to circuits. That's really the main focus of this unit, and the tool we're going to use to connect those two are topographic maps. So what is a topographic map? It's this, think of this as a landscape. A topographic map with all these lines, it takes the elevation, and each elevation corresponds to a line on this topographic map. So right here you see 20, 30, 40. This 20, every elevation on the landscape at 20 is traced out by this line. So every point on this landscape that is at a height of 20 is traced out by this line. Every point on the landscape that's at a height of 50 is traced out by this line, by 40 by this line. So to interpret it, you basically see like, oh, it's low to the ground here, low to the ground, lower, getting higher, 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 and this is your peak. And then this is also your peak. Another way to read this is places where you're crossing many lines in a short distance, like over here, it's like very steep. If you're planning your hike to the peak of this mountain, you'd probably want to take a less steep path. So what does this have to do with electrostatics? Well, first off, we need those lines of equal potential energy per unit charge, lines of equal electric potential. So first off, what does the electric field lines look like around a positive charge? Looks like that. Put a positive test charge over here, feel a force outwards, essentially. So where are areas of equal electric potential energy if I was to put a positive test charge somewhere? Hopefully you can kind of remember or think about it, but basically if I bring a positive charge from here to here, I'm changing the energy. But if I bring it from here to there, I'm not really changing the distance. It's a radially symmetric. So I have these symmetric circles, and these are lines of equal electric potential energy per unit charge. The last piece we need is where is high electric potential and where is low. So hopefully you remember close, that's where a positive charge would have higher electric potential energy. So that's where it has high electric potential. It has more distance to accelerate over, whereas compared to a test charge you put over here has just a little bit less distance. The last piece of the puzzle that we need is to associate high electric potential with high elevation. So this line right here is essentially our topographic line. And so what does the 3D visual look like? It looks like a peak. The positive is like a peak, and these lines of lower electric potential trace out this surface. What does this look like for a negative charge? So first off, remember, what do the field lines look like? Looks like this. Same as before, but pointing inwards. What do the areas of equal electric potential energy per unit charge, what do they look like? Same as before, radially symmetric. But a little bit different, where is high electric potential and where is low? Hopefully remember the difference. A positive charge here would have less energy than if there's a positive charge here, because there's a shorter distance for it to accelerate over. So this is low electric potential. This is higher electric potential. And so if we associate low electric potential with lower elevation, then what does this look like? It looks like a sinkhole almost, this bottomless pit. What about for this charge arrangement? What do the field lines look like? Points from positive to negative, so straight lines going across. But what do the lines of equal electric potential look like, those equipotential lines? Looks like this. These are areas where the electric potential energy per unit charge are the same. This is what I'm calling an equipotential line. It's a line of equal electric potential. Same height. So what does the 3D representation look like? Kind of looks like this. higher height, lower height, and changing elevation in between. Why are these topographic maps useful? Well, just imagine, what do you think would happen if I put a positive charge in this location and I released it? What would happen? We can rely on our analogy to gravity and say, what would happen if this was a slope, a landscape, and I put a mass there? It would fall down, and that's exactly what a positive test charge would do if it was allowed to move. It would move from high potential to low potential. Another way to look at that is you have those field lines, and the positive charge would feel that force in that direction. Just ignore this thing for a second. These are the lines of equal potential for a dipole, positive and negative equal charge. What do you think the surface would look like? The 3D topographic visualization? It would look like this, basically a peak next to a valley, or like a sink. What I want you to see is like a battery is similar to this. You have positive, you have negative. But if this was the case, then why aren't those positives just moving, sliding down the hill towards the negatives? Well, it's because a battery, there's this basically this big barrier between the positive and the negative, preventing things from sliding. So why is a battery useful? Well, we can make use of a battery with one life hack, with one trick. You take the battery and you put a path where the charges can easily move. And that's kind of like creating a slide around the barrier, through the barrier, under the barrier, whatever you want to say. And it's kind of like a slide. The elevation slowly changes, and if the positive charges can move, then they would move from high potential to low potential. And this isn't just a theoretical concept, it's something you can take a look at. What I have here is a AA battery. This is 1.5 volts. A volt is a joule per coulomb. Electric potential difference is voltage. So a 1.5 volt battery is a 1.5 joule per coulomb electric potential difference between these 2 points. And so when you connect wires to those ends of those batteries, there is a potential difference here in this gap. And when you put a path connecting them, you'll get charge flow. And so it could be a light lighting up, or it could be a motor, or your phone charging, electric toothbrush, or whatever. You'll get charges moving, and you can get them to do stuff. In summary, if you think of electric potential energy per unit charge, or electric potential as elevation, then lines of equal potential trace out essentially a topographic map that you can then interpret. And what do charges want to do? Positive charges want to move from high potential to low potential. And that's really the fundamental idea behind circuits. Thanks for watching. Hope that was helpful. Catch you next time.